Nobody wants to turn on. Is it okay? All right. So today we'll move on to something that we have started off as far as structures are concerned. Okay. Let me. Yes. Very good morning to all of you. I'm going to straight go to PPT. Okay. So I'm going to share this screen. Okay. Should I share the screen? Okay, I'll share the screen, but also let me do one thing. I need to get the chat on. Okay. All right. So we are ready to go now. So in yesterday's class, what we did was let's see if I can remove this guy. We looked at combinations, no? So if I have one spring like this, let's say, yeah, folks, just mute. I'm going to mute everyone. Oops.
சார்ஜ் இருக்கு கொஞ்சம் இங்கே உட்கார்ந்து இருக்கேன் அப்புறம் இப்ப சார்ஜ் கம்மியான மாதிரி தோணித்தான் நான் மாடி போயிடும் ஓ மாடியில ஃபேன் போட்டுட்டே நான் வந்துட்டேன்னா தெரியும்
Aditya, you have to mute. Okay. So if I have a spring of stiffness K like this, and I attach another spring K, then if I need to find out what would be the elongation for a force that is applied over here, or what is the force for which this is a unit elongation, what I'll get is F is nothing but the stiffness of the system of the springs, right? And we found that the total, let's say capital K, was equal to, let's say this is 1 and 2, then it was in this relationship, right? If I take this as K, right? So we call this as springs in series. I'm introducing like this so that you can use whatever you did for resistances directly for this. Okay, so on the other hand, if I have stiffnesses which are the springs that are parallel to each other, and let's say I need to find out the force for unit elongation, then I can find that K, let's say this is total K, is equal to K1 plus K2. Okay, this is simple. We understood this. All right. Now on the buzzer. Oh, I'm feeling good, Siddharth. Hope you're also doing fine. On the buzzer, supposing I have like this. Let's say this K1, K2, K3. And I want to find the stiffness of this. How will I find out? On the buzzer, I want to find out a total effective stiffness. This K1 plus K2, K2, K3. Fantastic. If the same thing is done in series, if it is done in series and I need to find out this for a unit elongation, it would be
Sum of reciprocals.
sum of reciprocals, right? This is something that I can immediately understand. This is not new to me. This is something that I have done earlier, at least in springs. I'm going to now make it a little bit more complex. Okay. So let me erase this. I'm going to have something like this, and I let you tell me how to do this. So I have one like this, one like this, one like this, and now I'm applying a force. Okay. Let's say this is K1, K2, and K3. And I need to find out the effective K. How will I find out the effective K? Fantastic. Somebody said 1 by K1 plus 1 by K2 plus K3 combined should be nothing but 1 by K effective, right? So what I do is I'll combine this and draw this to be, so I'll go methodically. This is K1 plus K2 by combining this. Now I have it in series. Now I can write K effective is equal to 1 by K1 plus 1 by K1 plus K2, right? Let me make it more complicated now. I'm going to have it like this. Just to simplify, I'll just put K only here. Okay. This is K, this is K, and let's say I'm now interested in K effective. How will I go about? You can also speak, doesn't matter.
Sir, 5K by 3.
How do you get there? Go methodically so that it's clear to
Sir,
everybody.
for first combination, these two springs are in parallel, so it would be
So
2K.
I'll take this and then make it into 2K.
Yes, sir.
Okay, and then I have K
2K
here,
and K in series.
2K in series, and then this is in
Parallel.
parallel. So what I'll do is I'll combine these two. I'll get it to be. I'll get it to be. I'll get it to be
So 2K by 3 and then K in
2 by
parallel.
3. So this will give me 2K by 3. So I have 2K by 3, and I have K here. I can combine this and tell you what would be the K effective, right? So I can keep on doing this. I can also now say, okay, these two are in parallel. Then I can do lots of combinations that I wish to. For example, I can do like this. I can keep on extending, saying, okay, there is one more here and one more here like this, and then one more right here like this, and one more like this. Doesn't matter. I'll be able to find out the K effective, correct? So this is the beauty of combination of springs. Okay, there are various ways by which you can combine the springs to get an effective stiffness. All right. So whatever stiffness it is, if I have to use a spring of K and I need to get some stiffness, K effective stiffness, then I can go about having different combinations and finally get whatever the result is. Fantastic, no problem. Now let's also look at how we graphically look at the response of a spring. So I take a spring, I pull it with a tensile force F. Let's say this is elongated by delta. Now, depending on the increase in F, how does the elongation happen? If it is a linear spring, let's say if it is a linear spring, then it's very simple. It varies linearly like this, and the slope of this curve is nothing but k. This is something that you know, all right? But I'm interested in not springs. For example, if I have a spring, if I have a spring, I may have a spring like this. The same spring of the same stiffness can also be very small like this. It can also be a spring which is the same K but different length, right? So it doesn't make sense when I shift it from spring to the real material. For example, if I have this material, this is wood, right? With the same wood, let us say I make something like this, something like this, something like this. What is common among all those? What is common among all those? On the chat box, what is the same? What is some all are made of wood. For example, I have this. Let's say I have this. This this is the same. What? Same. This is the same. Not K. This is the same material. Correct? Supposing I take a steel wire. Okay, this is, let's say, 1 mm diameter, and I take another. Are you able to see? Okay, I take another which is, so these two are nothing but this same material, steel. So what I want to find out is, instead of going ahead with this spring constant K, I want to come up with something that relates to material. Okay. So far, okay? Is this clear? How do I go about doing that? Okay. Now, let us look at what happens. Supposing I take this, all right? Now, I have one like this and one like this. I combine them this way, and I pull the stiffness of this will become the stiffness of this will become twice, correct? Why twice? Why twice? Why twice? Two springs in parallel is fine. Anything else that you can see, because this is different from a spring as such, right? This has one cross-sectional area. This has another cross-sectional area. When I combine them both, twice the cross-section. Fantastic. Yes, Ayush. Twice the cross-section. Or in other words, if I have one rod like this, let's say this area is A, and another rod or another spring, I'm going to call this as material spring, same cross-sectional area A, and let's say if I apply F by 2 here and F by 2 here, and find out the elongation, and I take another of the same material, but now with a cross-section which is equal to A plus A, and apply a force F over here, will I get the same cross-section? Will I get the same cross-section? I'm sorry. Will I get the same elongation? Sorry. I was wondering why there is no answer. Shall I repeat this once more? If I take two pieces of area A, small area A, and apply F by 2, but I take another, let's say, elastic band with 2A as the area and F as the force, will I get the same elongation? That's the question. Or in other words, I had two pieces like this, right? Now, I somehow merged them into one, right? Will I get the same elongation? The answer is yes, correct? Right? So in a way, if I have to now shift to material stiffness, I need to somehow remove this area part of it, correct? So instead of looking at force, I'll now change to force by the cross-sectional area A. Okay, so I'll remove this and introduce F divided by A. But F divided by A, I remember we did this earlier and we call this as stress, right? It may not be the same slope now, so I'm going to put it as K bar. The elongation remains the same, but now force is force per unit area that I take instead of this, right? On the other hand, if I take, let me just remove here. Oops, give me a second. On the other hand, let us say I now have the same area, okay? So let's say same area A. I have one piece like this, and I combine another piece over here. I need to draw same length. So I take another piece over here like this, combine them. This area is A, this area is A. This length is L by 2 and this length is L by 2. And let's say I apply a force F over here, I'll get an elongation. Yes? Supposing, let me do it this way, it's easier to understand. Okay, so let's say I have L by 2 and let's say I'm applying a force F. Okay, then there will be some elongation. Let's say it is a proportional spring. So if I do F by 2 here, then I'll get some elongation. Let us say now I take a length which is longer. Let us say L over here. And I apply the same force F by 2 over here. Don't ask me why I'm saying F by 2. Now, compared to this L by 2 and this L, how would the elongation be different? What would be the elongation, say, let's say delta 2 with respect to delta 1? Go ahead. It's the same, correct? I have delta 1 is equal to delta 2, although the lengths have now changed. So in a way, I can eliminate length out of this elongation so that it is possible for me to have the same elongation per length so that I extract the material property rather than the elongation per se directly. I'll repeat it once more. So let me just take it as F, it does not matter. Let us say I take a small piece L by 2 and apply a force, I'll get delta 1. I take a long piece like this, which is of length L, and I apply the same force F. Will L1, delta 1 be equal to delta 2? This is L by 2. I apply the same force. Cross-sectional area is the same. Cross-sectional area is the same. Then I'll get delta 2 to be twice delta 1. But that means elongation seems to be varying with the same material. This is the same material. Let's say this is rubber. This is also rubber. So I don't want it to change. I want this deflection to be the same as this deflection. What should I do? It is difficult for me to have these two elongations to be the same. But on the other hand, if I take delta 2 and delta 1, if I divide delta 2 by 2, I should get delta 1. Or in other words, if I take delta by L here and delta by L by 2 here, will I get the same value? The answer is yes. And therefore, I am now going to shift it to elongation per unit length of the rod or the cable or the thread, whatever, right? So I'm going to now introduce delta by L, and let's say this is K bar bar, okay? So what I have done is I have eliminated length L and cross-sectional area U. What are these? Just a second. What are these? What are these properties? If I have to call them as, what kind of properties are these? The length and the area. Physical. Uh, what other name can I give? What kind of property are length and area? Dimension. Very good. So it is dimensional properties, right? Dimensional properties, or I can say geometric properties. Okay. What I have done basically is I have eliminated geometric properties so that if you tell me the material, I'll attach a particular constant to that. It need not be a constant, but let us say it is proportional like this between force and deflection. If I take a material like this and do it, this K bar bar is irrespective of length or area, or in other words, the geometric properties. Are you with me? And therefore, what I'll do is, I'll now say elongation per unit length this is what I will call as strain. Okay. Delta by L. I'm going to use a symbol like this, epsilon delta by L. And here I have already used stress. So I have a strain to stress. I had something like this. This is completely a material property. So far, okay? Are you able to get the hang of it? What I did was I started with the spring. I said, okay, it's not a spring. It is a material like this. It is a spring made of the material like this. So I want to now zero in on the material. What shall I do? So I started to remove the geometric properties from the material characteristic and finally ended up with a relationship that could be between stress and epsilon. Okay, this is what I get. Okay, assume all these are proportional for now. We will change this later. Usually this is written as elastic modulus, though it is not correctly used in parlance. This is called the elastic modulus, and they use a symbol which is not K but E. Okay, so I'm going to remove this and say this is E. Okay, so I have sigma is equal to E epsilon is what I get, right? So if I have stress and strain, if I apply a particular stress and get a particular strain, it is possible for me to use these two in order to get E. Or in other words, E is equal to sigma by epsilon. This is the material property. Okay. Let's look at the units. This, if I use the Newton as the force unit, and I have to divide by area, so I'm going to use meter square. All right. Now, as far as strain is concerned, this elongation is in meters, length is in meters. I'll get a dimensionless quantity. So far, okay. Just spend 5 more minutes understanding this. This should completely get into your system. All right. Dimensionless. Okay. Usually what they do is, since this value is very, very small, they take epsilon to be percentage of the original length. For example, if I have something like this, let's say this is the length that I have. Let's say I have a measure, and let's say the measure is this much. Okay, I have 150 mm of this. Now, if it has elongated by an extent, I'll look at the elongation length as a percentage of the original length. Okay. So usually strain is expressed in terms of percentage and stress is expressed in terms of Newton per meter square. Okay. You can say dimension or geometric, both are okay. Now, is this unit familiar to you? Is this unit familiar to you? Where else did you see this kind of unit? Pressure, Pascal. So this stress is expressed in terms of Pascal. Okay, so far so good. So what we have done basically is we have now located a material property and looked at this more closely. If you're okay, I am just going to erase some of this so that I can move on till okay. All right. So let's go back to that bar. Okay, I have the bar. I have the bar. All right. Now I'm applying a force F here. This has a length L and cross-sectional area A. Okay. What I want to find out is elongation with respect to the force that is applied. Okay. So what I'll do is I'll start from here. I'll start from here. Now, what is stress? Stress is force by area, and that is equal to E times elongation per unit length, which is delta divided by the total length L. From this, it is possible for me to write delta is equal to F times L times E times A divided by. Are you with me? Shall I make it a little bit more clear here? This stroke. All right. Is this okay? How do you remember this, folks? How many of you know what is flay? How many of you know what is a flay? This is, rainy season.
Force, length, elongation, area.
Yeah, but what is flay in English? Flea, some insect. You go to marketplace, you see this kind of insect. right? So remember, I don't want this insect, so I cut it off, slash it. So remember it this way. Flay needs to be slashed. Then I get the formula FL by EA. Are you with me? This is just for you to remember. If somebody asks you, how do I find out the elongation of a simple bar? Flay, slash. Where do I slash? At the middle. All right? Okay, just something for you to remember. So far, okay? Any questions on the chat box? You can also ask orally. Simple, right? Okay. Now, what did we do? We did a few things. One is from springs, from springs, we went to continuous, let's say axial elements, right? Continuous or continuum, whatever you want to call it. So in a way, this constitutes the material that the element is made of. Okay. The other one is we have shifted from force elongation to and stiffness K to stress. Go ahead. Strain and elastic modulus. Okay. So we are going to use this over and over from now on. What is stress? Force per unit area. What is strain? Elongation per unit length. What is E? Stiffness of the material. Another word for that is modulus. Okay. This is only a very, very crude explanation I'm giving. We will refine it as we go on. Okay. Anything else? Anything else? Units. Stress is in terms of pascals. Strain, usually in percentage or a direct value. How about stiffness? Stiffness is nothing but stress by strain, which also has to be in pascals, right? So this is also expressed in pascals. Okay. So Newton per meter square, Newton per meter square, and this is dimensionless or percentage. Okay. What else? When I express like this, it is independent of geometry. Independent of dimension or geometry. Anything else that you can think of? Anything else you can think of from whatever we have discussed so far? Now, let's go back to this. Should it be linear curve like this? Should it be a linear curve like this? Let's say I test the material. I take this material and I pull. As I pull, I notice the elongation. So I pull with a force, knowing the force or measuring the force and measuring the elongation, I should be able to plot this graph, correct? Now the question is, will I always get it to be like this, a curve like this? Not necessarily, right? Not necessarily. It can be anything. Doesn't matter. Probably this is too much for us to digest. So probably something like this, which is not necessarily a straight line like this, right? Now let's see how the materials are when tested. Okay, so this is strain. Look at this. This is measured as a percentage of the original length. and this is stress in Newton per mm square. I'll tell you why Newton per mm square in a minute. Okay. So I can test various materials. Remember, all these are materials, nothing to do with structures as such. These are materials. This is a material, this is a material, this is a material. By drawing such materials, we get an idea of the comparison between relative stiffnesses and strength of materials, right? This is very useful for me for a later, for an application. Okay. Look at this very carefully. This is a carbon fiber polymer, CFRP, fiber reinforced polymer. And this is a glass reinforced polymer. This is steel that I'm looking at. This is aluminum. Look at this polyethylene. What some of your plastic bottles are made of. Very, very small, right? So let's now think these units. We decided that stress would be in terms of Newton per meter square, modulus would be in terms of Newton per meter square, and strain would be in terms of percentage. All right. Now let's take, for example, this. Are you able to see? This is a 1 mm. I can measure it. I just measured it. It's about 1 mm that I get out of this measurement. This is a 1 mm cross-sectional steel wire. 1 mm. 1 mm. Do you think I can pull it to a noticeable elongation? Do you think it can be, the elongation can be noticeable if I pull with hand? Yes or no? No, it's very difficult, right? Even a very strong person, remember I was a weightlifter, strong person, even then it's not possible for me to elongate more than probably a micron, right? So in a way, if I have to understand it, I'm going to just ask you to visualize now. Okay, will you just visualize? Let us say I'm going to now make a wire like this. Let's say I hang it on the ceiling. I hang it on the ceiling, and I want to make sure that this wire does not break when I put my weight on it or hang my weight on this. Okay. What is the cross section of this? 1 mm dia. 1 mm diameter. In fact, this is a little bit less, 0.8 mm diameter. This is 0.8 mm diameter. I want to now find out whether this can take my weight. Shall we do that visualization? What could be my weight, roughly? I reduced my weight by about roughly 20 kgs now from what I was about 6 months back. I was 85 kgs. Now I'm 65 kgs. So let's say 65 kgs. Okay. That means it is 650 newtons. So this wire that I'm thinking of using in order to hold me, right? I need at least a capacity of 650 newton. Okay. Let's look at steel strength. How will I measure strength? What will I do? I'll stretch it, right? So I keep increasing the stress over and over and over. At a particular point, it starts to give way. Okay. And that's starting to give way, I call it as strength. So far, okay? Because beyond that, it will not have the strength to hold me, right? Can any one of you guess what could be the strength in terms of Newton per meter square, it's a very difficult guess. Because remember, this is very, very strong. So I don't want to use Newton per meter square. I want to use Newton per mm square, so that it makes sense to me. The values make sense to me. What is Newton per mm square? It is Newton 10 raised to 6 Newton per meter square, right? These two are one and the same. This is 1 Newton per mm square is 10 raised to 6 Newton per meter. What is the word that we use for this? 10 raised to 6? Anybody? Fast. Mega.
Mega.
So I'm going to use mega. I'll borrow this word Pascal. So I'm going to use for stresses megapascal. MPa. Remember this word MPa. So the first question that you would ask is, sir, what is the MPa of this material? What is the MPa of this material? Immediately one would catch what the one is asking. Megatarini. I don't know what that is. Megapascals. All right. Okay. Now let's understand this. I have a 1 mm dia steel rod. What would be the area? Roughly, give me a rough figure. 3 mm square. Oh, it is dia. I'm sorry. It is 1 mm dia. The area would be roughly, let's say 1 mm square without much of a loss. It's a little less than 1 mm square. So I'm just going to assume it is 1 mm square. Okay. Now, if it is 650 Newton that it has to take, then I'm looking at 650 Newton that it should be able to bear within its 1 mm dia, 1 mm square. This is the stress that I'm applying if I'm hanging on that 1 mm wire, right? Now, if the steel wire is able to take this, then I can relate saying, okay, steel wire seems to have 650, at least 650 as its strength. Is this clear to you? Is this clear to you? Can somebody guess what would be the strength of steel wire? This is actually a high strength steel wire. A steel wire normally. What would be in terms of megapascals? 5 megapascals. Okay, one bidding over Siddharth. 10 Vaishnavi. Any other bids? 200 MPa. Who is that? Arpit says 200 MPa. One of them said 9, 4, 15. What else? What else? 100, 250. Nishan says 250. 900 MPa. Okay, you can go on now. All right. Now, these guys are pretty close. Nishan is pretty close. Arpit is pretty close. This is about 250 to 700 MPa, depending on whether it is high strength or this. Supposing I use this rod, which is high strength rod, I'm looking at roughly 700 Newton per mm square. Remember this wire, which you are not able to see properly unless I bring it as close as possible. This wire can sustain my weight. Think of it. All right. That is how thin it is, and therefore I go for megapascals. Any questions? Because the next thing that I'm going to tell you about is we have looked at strength. What else shall we look at? If we looked at strength, what else should we look at? The other S, which is stiffness. Okay, right? We'll come to stability. Stability, I'm going to go very slow later, but let's understand stiffness. What is stiffness here? If I have to understand the stiffness of this, what should I do? If I have to understand the stiffness of this, what should I do? I should elongate by a unit length, right? And find out what is the force that I have applied. Yes or no? So I'm going to do that in the next slide. Okay. So let's look at stiffness now for today's class. What did we say? The stiffness of the material now is in terms of Newton per meter square Pascal, right? Now, if I take a steel wire, let us say this is the ceiling, and now I'm hanging it. What is, let's see if you have some sense of dimensions here. What is the usual height of a room, roughly? Let's see how many engineers can answer this question. Budding engineers can answer this question. 12 feet, 10 feet, 3 meters. So fantastic, yeah. Vaishnavi, Anirudh, Harsha, all of you are correct. It's around 3 meters, 3 to 3.5 meters is the height. Okay. In terms of feet, it is 10 to 12 feet. Okay. So here I have about, let us say my height is what, 1.2 meters, 1.5 meters, whatever it is. Okay. I'm going to make myself a dwarf, 1 meter. Okay. So I'm looking at 2 meters as the length of this wire. Now if this 2-meter wire elongates by 2 meters if I hang, does it make any sense? No, right? What would be something that would be tolerable for you if it elongates? What would be the tolerable limit that you would give here? 2 centimeters. Okay. No, sir, 2 centimeters is too much. Let's say about 1 mm is what Karthik is saying. Okay, let's say it is 1 mm. Okay. What would be the stiffness of this material? Let's calculate. What is the stress? 650 Newton per meter square was the stress that I applied. Okay. Now, this is the stress, sigma. And I know what strain I have to get. What is the strain I have to get? It should be 1 divided by 2, right? 1 divided by 2. 1 divided by 2. 1 mm divided by 2. Correct me, yaar, correct me, correct me. 2000, right? 2000 mm, right? 1 by 2000 is what I'm looking at as the strain. Okay. Now, relating these two should be the elastic modulus that I require. So let's see what I get. 650 divided by 1 by 2000 is roughly, give me an answer, give me an answer. This is Newton per meter square. I should get 13 into 10 raised to 6, huh? 6 Newton per meter square. Correct? Is it 10 raised to 6?
Excuse me, sir.
Ah,
Sir, sigma should be 650 Newton by millimeter square, right?
fantastic, yeah. You got it. Ah, all right. Now we are talking into 10 raised to 6. So what will I get here? 10 raised to 10 raised to 10 raised to fast. 10 raised to 11, huh? 11 or 10, 11, 10. Okay. Or in other words, it is 130 into 10 raised to 9 or 130,000 into 10 raised to 6. If I have to tell the stiffness of the material of high strength steel, I can either say 130,000 MPa or this number itself is too much, I may probably go for just 130. So 130 what? Instead of mega, I would say, help me, gigapascals. So the elastic modulus usually is expressed in terms of gigapascals. So far so good, okay. For steel, it's around 250 gigapascals. What would it be for rubber? Any guess? Any guess? This is rubber, right? Any guess? Quickly. I have two more minutes to wrap up. For rubber. For an elastic band, the material of the elastic band, roughly what could it be? 100 MPa. Fantastic. Yeah. Some of you are thinking well. It cannot be in terms of gigapascals. I'll go into fractions, correct? It has to be in MPa. Sandeep said, of course, Sandeep should not be saying that. He's a TA. But anyway, Sandeep or Mohammed are very close. It's about 1 MPa is what you will get for this kind of rubber. All right. Of course, there is a variation. You can also have rubber that is more stiffer, the ones that are used in tires, etc., etc. What's the difference between this rubber and the ones that are used in tires? There is something that they do. What process is that? Anybody knows?
Vulcanization.
Vulcanization, yes. So vulcanization, basically you're connecting the dangling what do you say, chains of the polymer through nodes. Okay, this like a net. That's called vulcanization. Anyway, coming back to this, by vulcanizing, I may probably improve it to 10 MPa. Okay, a maximum that you can go is very, very small. But remember the difference between 1 MPa and 250 MPa that we are, 250 gigapascals that we are talking about. Huge difference. Okay, I want you to get a feel for these numbers. What do you think will be our skin stiffness? Quickly, skin stiffness. 1 mark. What could be the skin stiffness? 5 MPa. 5 MPa is too much. Yeah, you're right. You have to go into kilopascals, right? Perhaps about 500 or less than that kilopascals. Okay. Our bones probably a little bit better in terms of stiffness, but our muscles and tissue are of the order of kilopascals, hundreds of kilopascals. Very good. You got a picture now. This picture is very, very important, folks. Don't forget it. When I talk about steel, I talk about gigapascals. When I talk about rubber or polymeric materials, I talk about MPa or even below that, which is kilopascals. And when I talk about strength for steel and all those, I will talk about in terms of gigapascals, hundreds of gigapascals. What would be the wood strength? Any idea, roughly? Think about it. Okay. So similarly, we can look at different materials and get a feel for the stiffness and strength of those materials. I'll go further into it in the next class, but just to give you an idea of how it feels to say some number, 200, 300, 500, 10,000 and so on. Okay. Oh, you found it in physics lab. What fantastic, yeah. So it's around 10 to 20 gigapascals is what you'll get. But the point is that steel is so soft compared to wood is so soft compared to steel is something that I start to understand. Okay. We'll also explore what could be the very strong materials, very stiff materials in the next class. I'll encourage probably 1 or 2 questions before I wrap up. Any 1 or 2 questions? Quickly. We are running out of time.